representing company NutriScience. You might be asking, what is NutriScience, which is a very fair question. They're a Pewaukee-based pet supplement company. They're a startup. It's a group of veterinarian scientists and engineers. They're formulating high-quality nutritious products for pets. They initially started this to give their own dogs, their own pets, the nutrients they needed for long-term health, comfort, and happiness. Then once they did this for their own pets, they realized that impact, the first-hand positive impacts in their own lives, and they wanted to be able to provide that for other people. So that's what drove them to start the startup. So we have the problem statement here. Essentially, what they needed is they buy the powder supplement they designed from a larger bulk distributor. It comes in these big containers. They needed us to design an accurate dispensing system, as you can see down there. Take it from this larger storage and put it into a weight final finished product that they have there. A couple stipulations on this: they needed no more than greater 5% air. And then this solution that we designed needs to be food grade, easily cleanable, and the dishwasher safe. And these are all reasons because their current solution they have cheap moments. So this is the current solution they have. I'll make sure it's not there. It's just an over-the-shelf product that they bought. It uses what we call vibratory feeding. So you dispense the powder into this vibratory feeder, and then it's dispensed into kind of an intermediary weighing system, and then it's dispensed out the chute there at the end. It works, but there's a lot of things that could be improved. A couple of the problems: it's really difficult to clean, especially in that hopper there. It's got a lot of sharp edges, corners. Having read through the food safety standards myself, it is not food safe. Some room for improvement there. And then the vibratory feeder itself causes density-based separations, so the heavier particles get flown to the bottom, or the lighter ones stay at the top, which is not good when you're dispensing nutrients to pets. And the vibratory feeder itself causes dust cloud when it's in use. It's really noisy, and it has a really small capacity as it. And then the user interface over there to the left, it's not really too good. So a lot of room for improvement on the solution.
So lead us to our objectives, which is what our solution needs to accomplish to meet expectations. Starting out that the design should dispense supplement powder repeatedly and reliably over 5,000 cycles. It should be able to dispense between 48 and 630 grams of supplement powder. That's to account for different volumes, different types of supplements, and different containers that they need to be filling based on the orders. The design should be able to dispense powder within 5% accuracy. And Nutris prefers that 5% error is an overshoot, because they at least want to have the ingredients that they have on the nutritional label to actually be in the supplement. It should allow the user to fill jars in batches of 50 to 100 consecutive jars for high volume orders. It should include a hopper to contain 6 kilograms of bulk material to be dispensed. And then most importantly, what we agreed upon, both NutriScience and us, is the design should be easily cleaned, with the powder contact and components being easily removable and dishwasher safe. So one of their biggest things that their old solution didn't accomplish was cleanability. That's the most important objective that NutriScience has. Moving on to our constraints and what we need to adhere to while fulfilling those objectives. First, the dispenser shall operate on 120 volt AC power, to be able to be powered by a simple wall outlet. Dispenser shall be made from food safe material and adhere to NSF and C 2-2022 standards. Those are the food safe standards for the type of industry that Nutris is a part of, which is the supplement industry. That needs to adhere to those. Dispenser shall not exceed a total cost of $1,900 in testing, development, and production. Finally, dispenser shall not use bulk vibration to avoid particle density separation. So again, kind of what Jake was talking about, a big problem that they're ultimately had that. Now this brings us to our research. So we all dove into peer-reviewed articles, industry handbooks, and other educational websites on powder flow, and really condensed our findings into these bullets. The first being that there are 7 valves available to realistically satisfy our needs, being the vibratory valve, screw valve, solids pump, wave valve, rotary valve, discharge valve, and pinch valve, all pictured over there on the right. Another thing we found is humidity heavily impacts powder cohesion. It's important to know what kind of environment you're operating this in, if it's humidity controlled, if it fluctuates from winter to summer. For Nutris, they have a pretty controlled environment where they're doing it. May fluctuate a little bit with the seasons, but overall not too big of a problem. Also, testing is imperative for flow analysis. So pretty much any article or thing we found on some new development or just development of a powder system, they always said testing is so important. You can only do so much calculations with that much amount of powder. It's good to actually do testing and get good data for that. Also, gentle agitation is recommended to prevent arching of powder or clogging. Then finally, smooth, non-stick food grade surfaces are important in cleaning. that adhere to those standards that I was talking about earlier. They're just important for putting over.
So along with our peer-reviewed article research, we also researched some patents to get some design ideas for potential prototyping of our valve types. So the first one that you can see pictured here is a version of the horizontal rotary valve. Not pictured is the hopper in which the powder will be fed into one of these compartments. And as the rotary valve spins, it dispenses it into a hole into the container of the user's selection. This is designed for single portion delivery. So we also have the screw material dispenser pictured here. This is the hopper, and the application for this one is powdered tea leaves. And from the hopper, it would be dispensed into this tube in which an auger screw type would push pretty much fixed volume amounts of the tea leaves and then dispense it at the other end into another container of the user's specification. Finally, if we have the pneumatic pinch valve type, this is a top-down view that you can see. So the powder would be dispensed through this hole, and this one is air actuated. So this pincher can control the amount of powder dispensed at a time or just close the valve completely. And this can also be modified to be controlled using electrical components. So based off of our design constraints and design objectives, we made this decision matrix to choose the 3 valves that we would proceed with testing. And based off of our decision matrix, you can see that the pinch valve, the rotary valve, and the screw feeder scored the highest.
Like Lucas said, the 3 that scored the highest, we then moved into some prototyping with, because like Miles had said previously, from all of our findings, the research was great, but you need to do some empirical, some data testing with that research. So the first one that we took prototype was a screw valve. I kind of headed this one out. A couple of notes that we made across the iterations we did. Inclination of 15 degrees is pretty important. This is kind of an industry standard because it helps to put the powder back against the screw so that you kind of get more even on dispensing, not in those volumetric pockets that you see. We refined the diameter and pitch to get a flow rate that Nutris wanted through some iterations. We added agitation because we realized immediately that without agitation, it was going to be useless. And then in our final design, we added motorized control, so we could really modify the accuracy of the powder we're dispensing with some testing that we'll talk about a little bit later.
The second valve that we did some initial testing on was the rotary valve. This actually splits into 2 subcategories, being a horizontal rotary valve and a vertical rotary valve. Starting with the horizontal valve, this is used for more precise metered dosing, biomedical type applications. Usually have horizontal rotary valves, and usually, or what it is it's simply a horizontal type paddle wheel with fixed kind of pockets for metered fixed volume dosing. And the advantage of it is it's really good at stopping flow immediately. So the funnel or the powder will come through one side of that valve through the funnel, then out the other side will be the chute going out. And gravity really isn't a factor since it's top down, it's able to kind of cut off that flow immediately. I implemented motorized control for our testing. We chose this mostly for our testing. We also looked a bit into the vertical valve. It's used more in industry for kind of bulk feed options, kind of high volume stuff. And biggest issue we had immediately is it's a lot harder to stop flow immediately for that vertical type geometry. So we fixed on the horizontal valve for our actual testing.
The final type of valve that we prototyped was a pinch valve. The main benefit of using a pinch valve is that it isolates any mechanical components from contacting the working fluid, which in this case would be a powder. In industry, these pinch valves are typically applied in line and actuated with either air or a pinching mechanism. For our design, we designed around an off-the-shelf silicone kitchen funnel, which would offer us the area at the bottom of the funnel to choke the flow while also accepting powder from a larger hopper on the upper portion of the funnel. This design uses a servo controlling dual pinchers to choke the flow. And the main drawback with using the pinch valve is that it does not positively drive powder flow like the other 2 versions of our prototypes. Rather, it relies on gravity to drive the powder through the valve. Therefore, if we were to go with the pinch valve, it would definitely be imperative to have an efficient agitator in the hopper above. To quantify the performance of each of our valves, we set to do some prototype testing. Our first round of prototypes were relatively low fidelity and were just 3D printed and hand actuated. This allowed us to qualitatively determine the success in dispensing powder. Our second round of prototypes, which are shown here, are higher fidelity and actuated with motors and servos and controlled by an Arduino. This would allow us to gather data about the powder flow through each valve. To quantify this, we performed a quote-unquote step response of dispensing 60 grams through each of these valves while recording the mass over time with a load cell connected to the Arduino. That load cell data was then written to a text file for later analysis. We have a few short video snippets from each of these valves. You have the rotary valve there, and screw valve in the center, and finally the pinch valve. And so there's a load cell connected to the Arduino collecting the data for each of these valves. That data is shown here in the plot showing the step response of each of these valves. Most notably, the screw valve, you can observe kind of a very stepped response, which is due to the volumetric, the volume between each of the threads on the screw as it goes around. It dispenses a fixed volume of powder. You can also notice that the pinch valve and rotary valve are roughly linear and very similar in mass flow rate. In addition, all three valves had a very similar overrun, as each of them were shut off directly as 60 grams was sensed by the load cell. So from this data, it would appear as though the rotary valve would be the suitable choice for us, as it had the highest mass flow rate and one of the lowest overruns. However, our team decided that any of these three valves would likely be a candidate to potentially continue with, as the mass flow rate could be adjusted because that's a function of the geometry of each of the valves, and the overrun could still be minimized by adding a more robust control routine. Therefore, our team had to revisit the Q matrix to select a further prototype.
So, as mentioned before, the results of the testing showed very similar results between each of the valve types. But going back to our decision matrix, based off of our two most important things for Nutris is the ease of cleanability and allowing for simple changeover. That is where the pinch valve performs the best and by a large margin. So we decided to go with the pinch valve. And as mentioned before, even though the pinch valve didn't perform as well as the rotary valve in things like percent overrun and also time to dispense, those can be fine-tuned and controlled based off of geometry, constraints, or changes, and better control of systems. So as mentioned a couple times now, agitation was very important and was required. You can kind of see that graphic there is just a graphic of bridging, and the agitator was introduced to prevent that. You can see in the middle is a very simple agitation design based off of a hopper off the shelf that was used to hold the 6 kilograms of required material. And we analyzed the powder shear just to determine the torque of the motor needed to run the agitator. And this was modeled by filling the hopper with powder to maximize the amount of shear imparted on the agitator. And then also we analyzed it at startup case to maximize the amount of torque that had to be overcome. We computed the torque using 3 different factors. The first being the shear imparted by the powder, both by cohesion and also the amount of powder packed onto the top of the agitator. There was also the inertial torque from the startup case, and then finally the torque imparted by any bearings used. And we also used a factor of safety of 3 to account for any torques that were not included, and also for extra being able to modify the agitator, since this is not yet the final design. So based off of the torque that was calculated, we ran an FEA model. 316 stainless steel was used because of its very high corrosion resistance, and from our loading, we got a maximum stress of 1.9 megapascals shown at the corners and edges of the agitator. And since the yield stress for 316 stainless steel is 205 megapascals, the factor of safety against yield is over 100. Additionally, there was negligible shaft deflection and the maximum deflection occurred at the tips of the agitator, but it was only 0.02 of a millimeter.
So this leads us to our servo force transmission calculation. So now that we've decided on our pitch valve for development, we wanted to immediately try to spec out a good servo that balanced power to what we needed versus being too bulky. So what we initially did is we tested ourselves, found that closing force in the vicinity of 3 pounds on each side of the silicone funnel with powder inside is required to actually collapse it fully. So what we looked at for our actual mechanism is it's like how Zane mentioned, 2 linear actuators powered by that servo. So we wanted to first compute the force needed by each of those linear actuators, 6 pounds. And then we looked at the servo arm on how it is connected to get the torque needed. And a lot of actual servos out there only spec out the stall torque. And we're looking at the maximum torque required is in movement, it's active torque. So we took the rule of 30 to 50% of stall torque ratings for small RC servos are usually required, and specifically we can look at each servo on a torque speed curve specifically. But what we decided to do is add a ratio of 0.3 to our torque needed to look at the stall torque for that spec. Then finally add a factor of safety of 3 to get our final stall torque needed for our servo as 24.4 kilograms.
Just wanted to highlight a little bit about the electrical design. We created a full electrical schematic for all of the subsystems, which are going to be controlled by an Arduino, which the pinout is shown here. With this Arduino, we'll also be controlling that off-the-shelf load cell that will provide us real-time mass feedback as the powder is being dispensed. In addition, we're also going to include a small graphical user interface to hopefully provide a more intuitive user interface than our current solution. A couple other features, we'll also add a light gate for sensing the placement of a jar for automatic dispensing, as well as control over the agitation and servo placement. Control system, we have a typical automatic control system block diagram shown here. On the left-hand side, the user would input the desired mass to be dispensed on the user interface, which would then talk to the Arduino and tell the servo how far to open. The position of the servo would then directly govern the mass flow rate through the system and result in a certain amount of mass being dispensed. And then, as I said before, feedback provided from that load cell. The exact scheme of controller is still to be determined. It's likely that we'll have the controller saturate the servo for most of the time while the powder is being filled. And then switching over to something like a proportional control during the last 10 or 15% of the mass being dispensed.
So looking ahead to next semester, our future work will include an extruded frame design for the overall system. So you can see on that second picture is our pinch valve system currently as it stands right in the middle, but overall extruded frame design still has to be designed. Along with that would potentially include stainless steel paneling to make the overall design look a little bit nicer. The funnel design, we currently have an off-the-shelf funnel that we are looking at purchasing, but that purchase has not been finalized yet. So in addition to our funnel, we will be finalizing our agitation design to match said funnel, along with the actual agitator would be housing for the motor used to run the agitator, and also whatever coupling mechanism system that we use to attach and detach the agitator with the agitator motor. Then there's the system integration with the electronics. So just finding a place for all of the electronic components to go, finding places where the wiring will go, and then finally to tune the control system.
Like Lucas said, one of the future things we're going to be focusing on is the funnel development, because that really drives, our flow rate, the main characteristics of our design. What we identified right now is we need a little bit larger flow rate than the off-the-shelf one that we have. So we came up with kind of 2 ideas to alleviate this issue. First of which is pretty simple, just making a bigger diameter, larger flow rate. And the second one is kind of the oblong diameter of the current diameter, and that would be thought there is that the servo would better close with the arms that it uses right now. So we looked into silicone molds, did some research on that. We kind of designed our own molds and then polished them and ordered our own 2-part silicone molds. They turned out really great. We'll be testing them to see what kind of flow rates we get out of them, and really what we need to go forward with the company. And this is something we can use in our final product. It's good safe, so really great stuff there.
Here are sources we use for credit as well as our image credits.
Thank you, that's all we have. We'll open up to questions now.
You. One question I had was with your prototypes, which are very good, by the way. Did anything surprise you? Or did it kind of, the results turn out kind of how you predicted they would?
I'd say we were probably surprised about how linear those responses were in the step response. We had no idea, is this going to be a really smooth response or is it going to be kind of choppy and maybe clumpy as the powder kind of absorbs moisture from the air. So we weren't really sure how well those would respond, but they actually surprised us with being quite linear.
And then how much interaction did you have with the customer during this process, would you say?
A lot. After every design consideration, it would be going back to that. It would always back and forth between us, but really in the end, it was their decision to be made. So there was, I think, 4 or 5 meetings for us. That's really important decisions.
Great.
Do you have any plans for testing the effectiveness of the agitator and design of the agitator? Have you done any already?
We have not done any at this point, just because we haven't finalized the hopper design. So we're gonna be designing the agitator to match the hopper functions.
But in all our prototyping, we had adaptations to look at effectively. So we had some prototypes that we able to modify together.
What do you think is the biggest risk moving forward?
I'd say probably the agitator and fixturing everything, because it's going to be slightly difficult to have, an agitator motor on the top of our system, reaching down into the hopper while maintaining that cleanability and food safe aspect of the system.
If you guys take a look at different angles of the hopper yet? I guess just based off of injection molding machines.
Yeah, so
Yeah,
in our research, there was some articles on like specific hopper angles to match the type of properties of your powder. And they gave like pretty good ranges. Pretty much what's out there that we can buy is like a pretty good general angle for most powders. And since they have different types of supplements, not every powder is going to be the same. So it's something that we considered. It's something that we realized a lot of off-the-shelf stuff matches what we need, especially if we have agitation.
just for a single type of powder, or will other powders be used in the machine?
So it's several powders, but they're all pretty similar in, their factors.
Okay. I guess just a word of caution on the angle. Lots of injection molding machines are designed wrong, the wrong angle. There's something to be careful of. Which component is made out of 316?
The agitator itself. So this. Yeah, since it's on its own, it's kind of tough to see, but if you go to the future design work. So this is a rough model of one of the hoppers that we're looking at. And so the agitator would go down, the angle of the agitator would be, it wouldn't be in contact with the base of the hopper, but it would be very close to it just to prevent bridging.
Just coming from implants, 316Ls, a little more corrosive, but maybe it's overboard for what you're doing. It may be something to consider. Is there anything that can be done on controlling the humidity, or is that just more of a control?
We're gonna try to have this whole system be at least like sealed off at the minimum. However, a lot of it does fall on what their current environment is. One other thing that we're going to implement in the user interface is have just a simple temperature and humidity sensor so the user can at least see what the percentage relative humidity is at that moment.
I mean, ideally, we'd have a system that could control itself, but for the cost implications, it's probably not an option.
So like,
So the agitator has 2 prongs, right?
Yes.
Why 2? Why not 1 or 4?
That's just what we use for testing. I guess we haven't made that final decision yet.
Well, we knew that one probably wouldn't work for us because then it would be off-center. So we also went with two as a manufacturing consideration because we wanted that bottom kind of Y-shaped piece to be like laser cut and welded onto the end of the shaft, which would then be more difficult to do it for pins on the agitator.
Also not a very analytical answer, but it seems to be industry standard that it's two prongs.
Any other questions? Is it time for one more?
Do you guys have to worry about drying the powder at all, or is it ready to go?
When they purchase it, it's in bulk and it should be dry already. So I think that'd be a concern that's already made before it gets their device on.
Okay, thank you very much.
Hello, everybody. We are the Mechanism Design Competition Senior Design Team. My name is Rob. I'm Colin. I'm Dominic. I'm Austin. Get right into it. So we'll start with our problem statement. So the idea behind our project is we want to design a stereotype robot with a reconfigurable range. That means we want to be able to use a robot that has only two actuators for the planar mechanism, as well as one additional Z actuator for the third axis. Some other constraints that we have for this project is that it should be able to carry a load of 0.3 kilograms, and it should be highly repeatable and precise in its motion. So in the top right, we have a quick little video of an existing SCARA, and this is the typical SCARA where it has two revolute joints. And we decided to change that up by using a variable joint. So a little bit about the variable joint. One question a lot of people have is why pursue underactuated mechanisms? And the main reason is for its applicability and energy savings. So for the topology of our mechanism, we basically have rotation and translation with one motor, which kind of shows the benefit. This also can be expanded on with the operating range. So you can take the rotation operating range, and you can increase it with the translational operating range, and then you get the resulting operating range. So you get a wider area of operating use as well. So a little bit into the background of our variable joint. It's based off of Dr. Slayback's research paper that he did on it. It's a novel design, so from our research, we haven't really seen anything like it before, especially in other SCARA designs. And we base off of our design off the topology from his research paper. So he had all the kinematics done and everything so that we're able to fully simulate and model our mechanism. And then our actual background research more focused on SCARAs that are already out there and individual components for our robot. So some of the patents that we dove into, so in the top right there, we have what a modern SCARA robot is with the two revolute joints and then the Z-axis rod that's going to go up and down. And then we were also worried about moment arm for bending, just with all the weight out on the arm. So we looked into a belt-driven SCARA as well, so that we could have
both of our motors at the base, and then that would in turn make our arm lighter, and we would have less of a bending risk when it's in operation.
So getting right into it, this is our final working model or most up-to-date model that we plan to implement for solution. You can see here that we have our variable joint, and this is one that extends from a 4-bar linkage into a prismatic extension. And we have the first arm down there. For reference, this is where we're going to put the pneumatic valve, pneumatic cylinder for the Z actuation. We've yet to implement this in our final design, but it's just here for reference. We have the belt-driven design controlling both of the actuators at the base, so that you don't have the added moment of having the actuator all the way extended and also cantilevered at the arm. And we also have an example just to better understand the motion of the system that we're going to pass around. Here, where you can tell where it transitions from a 4-bar mechanism into that slider.
Now getting into the programming of the entire system. So the first thing to do, before we did any physical motor testing or any physical prototyping, is we created a MATLAB simulation that effectively simulated the inverse kinematics. So we decided to do this just to verify all of the inverse kinematics and make sure that we had the motion down completely. See, I have the video up here of the current state of the simulation. Little blue figure at the end shows the constraints and how it changes from just being a rotational joint to a translational. So it shows that it's variable. So this is effectively path synthesis because the user can input any points anywhere on the plot, and then once they hit enter, it will simulate the path of the mechanism. So on the bottom left here, we have some forward kinematics for the X and Y coordinates, which are going to be based on theta 1 and theta 2, which describe the angles of the two links that you can control, which will be controlled by encoder motors. And then on the bottom right, we just have two inverse kinematic equations, which are, again, corresponding to the coordinate angles. So a little bit more on that graph that you just saw. We have 3 ranges here. The outermost range is the maximal operating range. That's the solid blue line. The innermost range is the dotted blue line, is the minimum operating range. And the red dotted line is the transition. So something to note here is in a typical SCARA, that red dotted line would be the absolute maximum operating range, but because we have a reconfigurable mechanism and we can go from rotational to translational, we can extend outwards towards that solid blue line. So we're getting effectively more operating range. And the way that this works is exactly as I described. You start with this graph, you can click anywhere on this plot, and then once you hit enter, it will actually actively simulate the inverse kinematics and the plotting of the mechanism.
So a little into how we came to a design decision is we created a decision matrix based off of 4 elements of the design. So we based our decision matrix off of our prior research and just key components of the robot. So for the mechanical side, we have a gripper and Z actuation decision matrix. So we decided to go with pneumatic systems. That was kind of the best for our application. Another category was the materials normally used, so we decided to go with aluminum. It seems to be the most lightweight but rigid at the same time. And then the other components had to do with the electrical and programming side, because it's a pretty heavy part of this project. So we had decision matrices for the wiring, control board, the programming language, and the control interface.
So the mechanical design aspect of this project is really a core tenet that we want to look into, because without having this variable joint really work well, this project really isn't worth it. So because of that, we did extensive prototyping this semester. Our very first design family, we really looked into just trying to understand the mechanism topology and just get a feel for the motion. In the second design family, we kind of addressed some of the binding. We had in total 4 different prototypes and a bit refined the movement, but it still had some issues. In part due to it being constrained by a kind of a slot mechanism, and it would bind, especially on the return of the mechanism. This improved on the last design because rather than having 2 separate constraints that are different on the top and bottom of the mechanism, here and on the bottom, we kind of flattened that constraint to a single plane and then mirrored that, so it's a symmetric coplanar constraint system. That proved to work pretty well, but it still had some minor issues. So we did one final complete redesign, knowing what we knew from the other design families, and that gives us this final product. This is the one that we're passing around right now. It uses almost a captive wheel mechanism as well as a slider. And we feel that it's pretty polished. Right now, we've only done prototyping out of PLA, but our new product, we're planning on doing it out of aluminum, either machined or pre-printed aluminum. And, so yeah, this is our final mechanism.
Well, a little further into our design analysis, we decided to run structures FEA on it. So this was an early prototype that we had for the belt driven mechanism. So it just uses the belt to be able to kind of get an idea for how the system will move when it's fully connected. So we wanted to run an FEA on the base link and the variable joint and see how much deformation would occur and the stresses that would occur. So we decided to apply a 1 pound load in FEA to the end effector. This is to consider the payload, which is 0.3 kilograms, which results into about 0.66 pounds. And then also to account for the vertical actuator and the gripper that'll be on here. So like Nick said, we're going to make this out of aluminum. So we decided to do that as our material enhances. And then our requirements for the analysis was to analyze the stresses against yield, against the factor of safety of 2 for aluminum. It's just a pretty standard factor of safety to use. And then we also want to analyze the maximum deformation, which we decided to choose as 0.05 inches. This is mainly because we want this to be as rigid as possible, because any flexibility in this movement can be a problem for our controls when we get to that. So for the results of this analysis, we found that the maximum stress was at some of the bolt holes that we have in our design, and that was at around 12,000 PSI. So when we looked at the margin of safety against yield, this was about 0.68, which means that the maximum stress is passing for our requirements. More notably, though, we want to really focus on that deformation. So our deformation in our first analysis, kind of see here, this image might be a little small. We got about 0.15 inches of deformation. So that yielded in a margin of safety of negative 0.66. So that means we needed to redesign this so that it can be a little more structurally sound. So for the redesign, we decided to take our base link and increase these aluminum extrusions, which are square, from 1/4 inch square to about 3/8 inch square. And then we re-ran the analysis. So looking at the stresses again, even though they were half before, we decreased it from 12,000 PSI down to about 5,500. This already met our requirements, which we really need to focus on that. But for the deformation, we ended up decreasing from 0.15 inches to about 0.04. So this yielded a new margin of safety of 0.28 inches. So that's proved that a redesign was beneficial, and hopefully that'll help with our further design analysis.
So getting back into some of the programming for this, the initial part that I talked about was purely just mechanism simulation and for demonstration purposes. So now we're going to get into the physical aspect with motor control. So this meant the transition from MATLAB to Arduino C++. So for this entire system, we're going to be using 2 ESP32s running Arduino on them. For the first microcontroller board, it's going to be closed loop PID control for position of 2 encoder motors, as well as the inverse kinematic calculations. And then the second microcontroller board is going to be taking user input. It's going to be displaying relevant information like position and velocity, and that's going to be in the form of this touchscreen display here. So we'll have 3 menus on here. This touchscreen is pretty user-friendly. You can click the button, and then it brings you to a new screen where you can then control X and Y plus or minus for your position, and then also control the vertical actuation as well as the suction gripper, which is going to be hooked up to a vacuum.
So because it's an actuated robotic arm, the electrical subsystem is really crucially important. This is a high-level overview of how we plan to actuate the final arm. Our main controller is ESP32 S3. If you skip to the next slide, we can go into more specifics as to how technically implemented. So at a lower level, we have in red our ESP32 and all the circuits. There's black in that. The blue section, we have a power supply because we operate at different voltages for motors, the controllers, and user input, and the LCD. And in the green section, we have the feedback for the motor limit switches, so we know where the conditions are. On the next page, we have 2 identical motor drivers in blue. This is how we're going to actuate just the 2 DC motors. We have the sections in red that are the incremental feedback, so we actually know where we are in space. And in green, we have the I2C protocol, so we talk between ECP32 on the control board and the ECP32 on the LCD display. So putting all this together, we wanted to put it into a single PCB, so it's nice and polished and professional. This is what we came up with, and it's all on one board. And we currently have this sandwiched to the back of the LCD display. And we're not sure if we're going to actually mount it like this in the actual implementation of the project. But right now we have it all in one nice working functional little sandwich.
So now to get into some of the pneumatics and vacuum, we're gonna have our air compressor supplying air to a 3-2 solenoid valve, which is gonna control our pneumatic cylinder. And then we're also gonna have our vacuum pump to a 2-2 valve, and then that's gonna end up going to our suction gripper. So for the pneumatics here, we chose a 7/16 inch bore diameter, just so that we can keep it pretty small. For our load capacity, we didn't need a huge cylinder for this. 3-inch stroke length. We wanted to keep our robot arm on the smaller side, but still big enough for demonstration purposes. And then our air compressor is pretty quiet, but it's still able to supply enough PSI. So our cylinder, just for scale here, with the 3-inch stroke length. And then because our air compressor doesn't need a tank, because our cylinder is so small, we're able to keep it on the smaller side as well. And then now getting into the suction gripper, we were able to find a pretty compact vacuum pump here with a suction and a little bit of spring there, so that we have some clearance when we drop down onto the object. With this vacuum pump, we were able to pick up over the 0.3 kilograms, which passes our specifications. And then we needed a little bit of like tissue paper on the end of the suction cup, so it didn't get stuck once we turned the vacuum pump completely off. So that's something that we're going to look into a little bit more in the second semester, is having somewhat of a like porous end surface there, so that we're not just coming down, suctioning, and then having it stuck on our object. And then we wanted to get into some of our learning experiences for this project. So personally, for me, I didn't have any experience with pneumatic systems at all coming into this semester. So it was a little bit of a daunting task at the start, but based off kind of the problem solving that we've learned here at MSOE, I was able to take it one step at a time, finding a cylinder that was going to work, and then also figuring out which solenoid valves were going to function best for our system.
On a similar note, probably the biggest thing that I've learned is going through the PCB design process. I've done PCB design before, but nothing really to this complexity. It really gave me some valuable experience, especially working ECP32 controller, which I feel is very applicable to any range of projects. So this was the biggest thing that I really got out of this project so far this semester.
The biggest learning experience for me was the applicability of FEA. Being able to take one of our early prototypes and run a quick simulation for it based off of some design requirements we have, that is able to aid our future design is really beneficial. And I could use that in a lot of areas of my career.
Lastly, the motion controls implementation. So like I mentioned earlier, I started off working in MATLAB doing a simulation, and then later on I went to the physical control, which required me to translate that into Arduino C++. So I found it interesting to work with two different languages that provide a similar function, but have a very different way of approaching it, solving that problem. So for our semester 2 objectives, the main things that we want to work on are to finalize the CAD model. So we have a pretty good mock-up of it right now. So if you want to move forward with one solid choice and just make sure that we can fabricate that design. The next thing is to obviously construct that prototype and start working on not just individual components like we have been doing, but try to get everything working together as a full system. We also want to fine tune our motion controls. That's going to be more PID tuning and just more looking at the inverse kinematics and how it's going to link up with this controller. And lastly, we want to enter the ASME SMRDC competition, which is going to be happening in August.
You.
You consider, how did you consider the joint deformations or sloppiness in your deformation calculation?
We just used a constraint at the base as well as the joint connection in FEA, so kind of modeled it as two beams. So to try and simplify it as much as possible. And then we did it in the fully extended position as well. This is just because this is where we thought the max evolution.
So how are you accounting for the joints themselves? Are they pretty considered perfect?
We consider them to be rigid joints as much as possible, just to kind of see what that deformation would be. And then
And how much weight does the cylinder and associated hardware add to the end load?
it's about 0.35, 0.33 pounds, and not very much. The payload was the major contribution to the weight that we put at the end effector.
Did you consider venting the suction instead of having it less effective when it's shut off? Because I know you had a two-way valve.
Yeah, so we started out with the like 3-2 valve, like how we have the cylinder hooked up, but we were losing some of our suction pressure to the exhaust port. So then we decided we don't have the 2-2 valve yet, but that'll be something in the second semester that we continue to test and make sure that we have the right configuration set up for that.
What is typically picked and placed with this kind of setup?
Biggest application in industry is probably your PCBA application built situations, because you have tiny little components that really require a high degree of precision. And it's just really repeatable tasks that really need to be fast. So that's probably the biggest application, but it could really range from anything on a plane you want to pick up on location and place somewhere else.
Is there a min and max weight you have to consider, or it's used for so many applications, it's hard to.
It's hard to say because it's used all over in industry versus our ones just chose 3.3 kilograms are given that by our customer. So you can very much scale the system up or down as needed.
Is there a target media for the prototype testing?
I don't think so. It was for testing. This was like 0.35 kilograms. And it was probably bigger than the objects that we were like planning to run our like demo on, but just kind of weight wise, we were able to test it in on flat surface so that our suction would like be able to functionally pick it up.
Is there a concern that if you're talking about an object that's not, like it has a lot of roughness to its surface, that the suction won't be able to attach to it?
That is a concern, but the core focus of this project is in exploring the actual variable joint and less so the actual gripping mechanism. So yeah, that is a concern, but we really want to focus on just saying this is a novel concept that actually has an application in industry. So that's less of a concern, but it is something very hard to be doing.
Any considerations on wear, since it will be, I guess, used, the cycling would be a lot, the wear, you have more of a sliding friction than a rolling friction. Material you have to be, aluminum.
Oh, yeah, so our final product, we're looking into either 3D printed out of aluminum or machining out of aluminum. We tried to cater the last family, design family, or so you can carry it over without requiring full redesign of aluminum. That is a concern, especially with the 3D printed aluminum. We're looking at that right now, but we're still kind of in the prototyping phase with just PLA, so
Might be
something for that.
interesting to have kind of like a bearing that pin, or I don't know.
Yeah, for now, all we did was just essentially use screws and that would loose fit to the top joint. So it just strains it, but it could be a lot better in the final if we're planning actually.
So I see you got like a bunch of these prototypes and it's pretty smooth, but have you tested it with any weight on the end?
Do some way. Biggest thing right now, just trying to get the planer mechanism to work nice and polished, and then work on actual weight. Like we've done some examples of that. Like with the most recent one, we do have a bit of issues, but we think that's mostly chopped up to tolerancing with the different prints, which we planning and readdressing. next semester and just dialing in how, because that's where most of the sway is kind of coming in with the.
Another thing to add to that too is we kind of did our FE analysis on this position, and then this is also another critical position to consider is when it's out here, because this will create torque on this joint. So that's just another thing that we want to consider. Or we just put up those nice. But so we'll probably look into that next semester as well.
And then, so you talked about for the workspace, how it has like the extra reach. Where would the standard Scara robot be able to perform better, or what, or can it reach positions that this machine cannot?
Yeah, so going back to this image here, typical Scara robot will be able to reach this minimum range to this dotted red line range, but because we have a reconfigurable mechanism, go from rotational to translational, we can extend all the way to the solid line. So it's essentially the same operating range from the minimum standpoint, but then we're also getting extra action.
So even though, on a standard Scara, this motor can go full 360, so they can still hit all the same positions.
Yeah, and that was depending on the strengths of our first motor at the base. I would limit the theta one, which is angle of the first beam.
Is it typical to use DC motors as opposed to stepper motors on these applications?
Biggest reason why we chose these separate our DC motors is because we have a lot faster speed, extensive gearing and stepper motors. Because we're using incremental motors with that active feedback and a closed loop system, we really didn't see the appeal of stepper motors because they're a bit lower resolution. I mean, we still have steps, incremental steps, but we think that brush motors is a better approach, especially in that closed loop system.
In your force calculations and the input for FBM, did you consider any like dynamics loads? Because I assume you have high angular acceleration. I'm not sure about like the velocity, but like, any centrifugal force or other forces from like dynamics perspective.
So for that FE analysis that we did, it was just a static configuration. So that's why we also wanted to explore other configurations too, and analyze when the actuator goes down, the impulse that would create. So that is something else that we also want to look into. And probably be another addition to what we could do.
Any last questions? Thank you very much.
Finally.
Otherwise, it'd just be. Have to, we have to have that one.
Yeah, so like immediately after. I mean, my friends.
Probably could have passed that out already. Probably.
Like that's like.
Then, yeah. Because we were communicating. But.
See if I can use it if I can.
It's true. Yeah.
But I don't know if it maybe it's like money.
Yeah, is that one? Yeah. 7 more. And then I'm done. Sleep. Yeah, tomorrow early in the morning. So, 5:30. It's our flight. At least when I checked 2 days ago, I might check again, but I think we'll just park it in the kids a lot. It'll be like. Yeah, it's not covered though, that's the problem. Brushes, 3 burgers and stuff. We plan on leaving like our winter coats in there. Because it's gonna be warm in Oklahoma. But so we don't wanna bring them with us. We put them on, we come back, it was fun. So when you find out what. So, this is full. Oh, I'm sorry. Unfortunately, it's very complicated, so anything can happen. Just like they just want to be hope. I think just operate. We're actually normally get. It was good to at least take your chance. Since you don't even understand. Yeah, you need some fast. It's partners that help you.
No, it's not case, not just that. I know. I feel like I can actually. I don't.
Okay, you can go ahead and get started when you're ready.
Hello, everyone. Welcome to our presentation here. automated monopoly system. So we're gonna kind of walk you through everything we've done for this semester and kind of everything just kind of compiled together. Have you done?
So we want our design of a monopoly board to be that enables gameplay for individuals with mobility challenges. So it should preserve the look and feel of a standard monopoly board. And then the dice rolling and the token translation are going to be performed via onboard actuation from the mechanical system. And then everything else is going to be managed through the user interface.
That's the rules, like Mason touched on, come from, like using the standard Monopoly board and its rules to make the project happen. Like I said, the dice rolling, the token movement needs to be done automatically, and needs to be done actually in the physical space. Everything else, like banking and properties and the like, is gonna be done on the mouse only digital interface. And that way, everything can be operated using just mouse clicks, and people with like eye tracking devices are gonna be able to play it as well. We want our systems to all be appropriately safe for the project, and it needs to be able to run for at least 1 hour of continuous gameplay. We want it to be user friendly.
So before we get into everything, the first thing we want to do is split the whole project into 4 major subsystems. So first we have the mechanical subsystem, which is going to be working on the actual actuation of any of the game pieces. We have the dice rolling subsystem, which is exactly what it sounds like. It's going to be working on rolling the dice. We have controls, which is going to connect our mechanical and dice rolling subsystem to the user interface. And our user interface will be controlling the game, communicating with the controls, and providing the digital interface for users to interact with. So this is our current state. Just before we just want to show you this, just so you know where we're going throughout the presentation. So we have our current core XY setup here on the left. We have our user interface on how people will be actually playing Monopoly, and then we have our current dice rolling mechanism down here at the bottom. So first off, at the beginning of everything, we wanted to really try and be creative. So before we really started doing any real background research, we all decided to go in and do initial design sketches of everything. So here on the left, we have an articulated arm robot. This arm will sit in the middle of the board off to the side. It's just like a pick and place robot that you would see kind of like the previous group was showing. Then we have almost a 3D printer style. So instead of the head of the 3D printer placing filaments, instead it's another pick and place robot. We have this underboard planar stepper. So instead of the 3D printer being on top, we kind of put it on the bottom, and we have a magnet actuation that'll be able to grab the pieces and then move around the board. I had this idea, what if we just put all the pieces in little RC cars and drove them around the board instead? And then for any of you that have seen the old Jumanji sequel, Zathura, the game board in that one, it's got grooves that each of the pieces sit in, and they drive around the board. And I was thinking maybe we could cut grooves into the Monopoly board and control it that way.
Some more designs that we had were like kind of like the last group with a tooling design where they can both rotate. So I can get along all those. And the head design will just kind of come in and scoop off the piece. For a dice roller, we have like a clear cube that just has a motor attached, so it just spins a cube, and then we can read the dice from the camera underneath it. We have a tilting dice roller, which this part translates up and down, and tilt the cups, and then after the dice are rolled, a piston will push like the landing zone up, so it slides back into the cup. And then on this, we have a gantry, so it can move along the X and Y direction, and then for the head, we're going to use a suction piece just to pick up the piece and place it down.
Some more design sketches we're gonna have like a track robot movement, where the blue here would kind of be where the robot would kind of go around the Monopoly board with a light barrier for safety. And then the gripper design would also kind of be just kind of like an elbow here, where it would come and grab a piece and then kind of be able to pick it up and move it to where it needs to be. The other robot over there, the overhead one, would kind of be just like the one stationary one, where it'd be a pick and place robot with like a 3-prong gripper that'd be able to pick it up and move it to wherever it needs to be. Some dice rolling mechanisms, here the robot one, where it kind of being up, sort of like this elbow here. It would kind of throw the dice, and then there'd be another mechanism to push it back into the cup so it can reset.
And then this popping style one where it kind of be like cams on a motor, where they would just kind of turn and shake the dice. And then on the top there, see that they have a camera over top to go read whatever that dice were, whatever would stop that mechanism.
And then the last initial design sketches we had were, first off, the blow magnet, which would have like a XY step system underneath with the magnet that heads with pieces. There's a claw machine one that would be steppers above the board and have like a claw piece attached or claw attached to the head of the pieces to move them. Above magnet, it's basically below magnet, but just above the board instead. And then a couple different, other dice rolling some ideas where the bouncing piston roller, where the motor would turn linkage and cause the platform dice around, bounce up and down and roll the dice. And there's spring loaded one where the motor would pull like a string or whatever to compress the spring and then it would release, causing the spring to stretch and the dice would roll after that.
So all of that was done prior to doing any background research, searching the internet for anything to find. So after that, we looked at some different patents and just any projects people had done in the past at all. So here we kind of found some different designs for robot arms. This here is a video we'll show later on. This guy actually kind of automated the game similar to how we chose in our approach. And then we kind of found some for dice rolling. Another one that was also very similar, but chess instead of Monopoly. And then also some different ways to be able to read the dice as well.
So now we're gonna get into the actual different subsystems and the design process for those. So first off, we have the mechanical subsystem. Out of all those ideas, we kind of boil it down to, we really like the underboard planar stepper system, and we like the articulated robot arm. For this, we just did your typical decision matrix and looked at weighted averages to determine the score for each of them. So we wanted to look at ease of construction, reliability, repeatability, cost, board visibility and cosmetics, accuracy, precision, and technical feasibility, how easy it's going to be to build. So as you can see, after we all voted and we took an average of all that, the underboard planar stepper system was kind of a runaway winner here. So next what we had to do is we needed to pick an actual planar setup. There were a lot of options. We have HBOT, dual drag gantry, a linear delta, cable driven planar, which is kind of cool if you think of like the cameras in the NFL that like sit over top of the players. It's the same system. But the two we really liked were the basic XY gantry, which is like your very typical stepper motor XY setup, and then the core XY, which is kind of a new system. It was developed about 10 years ago and it's an offshoot of the HBOT. So looking at these two, we wanted to compare the advantages between both systems to determine which one was going to be best. So looking at our core XY, it's going to be faster and smoother than the basic XY gantry. It's going to have reduced vibration, some flatter geometry, so we can fit it in a more confined space. It's going to be better for larger work areas, which is really good for our Monopoly board, which is going to be pretty large. And then we have the dice roller off to the side that it's going to need to control. So it's good for that. And a big thing is it has stationary motors. So if you look at the XY gantry, on this perpendicular y-axis, the motor actually sits with the gantry, which is going to cause a lot of inertia in the system. Whereas on the core XY, both of the motors are stationary and everything is belt driven from there. However, looking at the gantry, you can see it's just quite a bit easier. It's easier to construct. It's got a simpler belt pad. It's more cost effective. It'll still be adequate for our use case, and it's less sensitive to alignment here. So that's kind of the big problem with core XY is it's great once you get it working, but it's kind of difficult to get it working. But we felt like we kind of had an opportunity here to do the best project possible rather than what was going to be the easiest for us. So we actually decided to go with the core XY because we felt like the benefits were going to outweigh any of those alignment issues we might have down the road. So speaking of some of that background research we did, we actually found this video. I'm not even going to try and pronounce that guy's name, but he's from the Netherlands. He's a mechanical engineer, and he developed this game called Clockwork Derby. And if Caleb wants to play it here, you can actually see it served as like a fantastic proof of concept for us. So he's actually able to use this core XY bot to move the pieces around. And one thing that we thought was really cool is it can actually rotate. So you'll see later on that's a feature that we're going to try and implement into our system. So this is our current build of our core XY. It's assembled of a frame of 30-30 aluminum extrusions. It's got a custom belt path. It's connected by some aluminum rods in the middle here and then perpendicular, and it's got a head assembly in the middle, which will be our magnet that'll actually grab and place all the pieces. We wanted to just make sure that our motors, our steppers were gonna be viable for this. So we did a really basic calculation. You'll see why in a second we were able to make it so basic. But we basically just wanted to see if the torque was gonna be enough. We got this weight after Elijah had finished building the stepper head. And then we said our acceleration was gonna be about 1 meter per second squared, which is pretty typical for Core XY. They generally sit around 0.75 to 1.5 meter per second squared, so that's gonna be plenty for us. And then we estimated our force of friction at 1 Newton. And this is just because we use low friction, high speed bearings for everything, so 1 Newton of friction force is gonna be plenty. So this came out to 1.6 Newtons. Then we looked at the torque and we basically just said C is gonna be the distance that the belt travels for every step of the stepper motor, which is manufacturer provided, which is very nice, of 0.04 meters. We divided that by 2 pi and we got a torque of 1.02 Newton centimeters. Now, the reason that this ended up not being that big of a deal is if you look at our NEMA 17 that we chose, which is just a very typical option for a lot of these Core XYs, we had a factor of safety of 45 for 1 motor. So we weren't going to be anywhere close to over torquing or under torquing the system. So we didn't really feel that it was all that necessary to do any more calculations there. And then these are just some pictures of the belt pad setup. So we have our base here, which connects to we have our motor, which then it'll connect to the bases on the other side. And then we have these middle pieces that'll support the stepper head in the middle. So next thing we wanted to do was we needed to look at the actual kinematics of a Core XY. Turns out it's actually incredibly simple. There's some great work done by some students and a professor at MIT who actually developed the Core XY system. And it all boils down to a really nice equation where we can calculate X and our Y position just by looking at the distance that the stepper travels per step. And we can plug that into A and B, and that'll tell us where the stepper motor will be or where the head will be at any position. So if we actually play this, Mason put together a simulation where we incorporated this math into a Python script, and we were able to move the piece along the board while using these delta X and delta Y calculations. And if some of you are wondering what the dots in each of the corners are, that's going to be specific piece placement in a way that we plan to organize the board.
So moving on to some designs for the head. So here I had one design where it was pretty simple. It was just a base sliding mechanism where a servo input would just right to the up position. It would engage the magnet, and when it came back down, it would disengage from the magnet. And then kind of down here, a little similar with being a track magnet, where the servo would return and it would go along a specific path. So it was easy to know where to be at any given point. And then at the end of that track, it would connect, and there would be a magnet that it would interact and be able to right to the engaged position where to connect the piece. And then also the one we ended up going with was the piston-like head, where you kind of have, this would be the servo input here, and it would kind of have a connecting rod sort of connection there. And then this overhead area would kind of act as a cylinder, and it would push the piston kind of up to the engaged position when we would right the servo. And then also, as we mentioned earlier, with the magnet or the motor to turn the pieces, that would kind of be housed in this area, so that we could just right or turn a motor and it would turn the piece when it was engaged in the up position with the magnet. So this is kind of the current state. This was my first design. The total height from the bottom to the top of this would be the engaged position, was about 2.4 inches, with this magnet section traveling about 0.37 inches, which is pretty small. So then I also tried to do a torque calculation for the servo, which ended up being relatively small, but still we wanted to make sure that it would actually work. So here's kind of my governing equation here, and then defining what my inertial force was, with the assumptions that just due to the size of the head compared to the overall Core XY, there's a pretty negligible load on the entire system. And also that the acceleration would be constant, because we would hope that the servo would move at a relatively normal speed. And also just kind of off of some SolidWorks tweaking, estimating that the servo would travel between 175 degrees and 135 degrees. And then I also have the position here that reduces to kind of the torque, and then its respective derivatives as well. And then, so also I needed the mass of the mass of this as well, and also the length and the radius of these two links respectively. So to get the mass, I created a custom PLA material into SolidWorks to try to estimate the mass through SolidWorks. There's not really great ways to find PLA material properties. It's just kind of like a broad Google search. I found a couple different areas that had stayed what they were and kind of took some averages of those. And then use that to calculate mass. And then from that, I got that our max torque at a position of 135 degrees was about 2 times 10 to the negative 5th Newton meters, or 0.002 centimeters. So then this was my second design, another just a redesign of it. So I added the linear bearings to the bottoms here that would go onto the linear rails that would actually mount to our core XY system. I also added extra supports for the servos on those sides. If you saw the other one, there was only one link that would, when the servo would run to the opposition, it would engage. And we worried that it would be too much of a torque and that the force would be unevenly distributed. So I kind of added some extra supports on the sides, try to account for that a little bit more. Then we also reduced the overall head of the magnet and the whole mechanism itself. We had an issue, we thought we would have an issue where it would be too tall. And so we tried to make it as short as possible. So this was able to reduce the entire height by about 1 inch from the other one, which the entire thing was only about 2.5 inches. So kind of cut it in half just about. And then we also added placeholders right there and there for where the belt tension would be. We don't know the exact kind of dimensions and specifications of what will be for them. So they're just kind of 2 placeholder blocks of where we think that they want to go.
All right, now switching up to look at the dice roll a little bit more. We zeroed in on 3 different styles we were going to do our decision matrix on and decide between. And the popping style roller, which would be stepping motor, turning the rod, should hold the platform with the dice down, and then release, it would slip out to release, and the spring would go, and the dice would roll. The cube roller, which was mentioned earlier, where just the motor would turn it and the dice would be able to be right in there. And then the robot arm roller, which would be more of an option for if we chose the robot arm, because it could come pick the cup up and then dump down to the tray. And then once the cup was returned, the tray would be tilted up and the dice would pour back in the cup. We have the same criteria for the dice roller as we did for the mechanical system. And you can see there that the popping style had the highest averages of the 3 styles. However, not long after we had done that, we decided we wanted to go in a different direction. We wanted to do something that actually roll the dice onto the physical, like either the board or the table or the physical tray. And that could be driven by the same mechanical system, so we didn't have to spend extra money on motors and things alike. So that was one of the first little concepts of the dice roller. It looks a lot like a catapult, but that was early on. After some changes and iterations, that was a prototype that was developed. That purple piece you see there would have a magnet attached, and that's where the head would come over and attach. It would pull to the right, moving that link along the slot, and that would cause the cup to go up and tilt to the left and roll the dice. Here is the current state of the dice roller. You can see we have the roller mechanism there and also the return. The dice return is basically just a plow that sits on the tray for the dice, and it'll just, once the roller has been returned to its initial position, the head will come over and push the dice back in. We've got a couple of kinematics equations there that can be used to find the angular position of the roller and the angular velocity of the roller, since we will know the linear position and speed of the head. So we're controlling.
So we go into the controls of the subsystem. There isn't a whole lot in this area because a lot of our controls is pretty much like the physical wiring and all of that in the system. So we have here just kind of our microcontroller selection, kind of the same design matrix here, kind of going with the price, the pin count, the camera compatibility, and the online simulation availability. From that, we had the ESP32, which is this picture as well.
So with the dice detection, I found an article online that uses OpenCV with blob detection algorithm. So what that does is once it detects the blob, it assigns it an inertia ratio, which basically just says how circular that blob is. So then we can filter out any of the blobs that we don't want that have a lower inertial ratio. So we can only get the ones that are on the dice, since the dice blocks are pretty circular. And then after that, we can just use a density calculation to kind of cluster those blobs together. Then we can get those dice values from there. With the piece detection, after some research, I found something called YOLO, which is you only look once, which is a computer vision model, which you train the model by taking a whole bunch of pictures of the board and the pieces and different rotations and lightings. So then after you train the model, on the right, you can see that there's a bounding box with a car, and the number to the right is the confidence value that is assigned to it. So you can filter out anything lower than like 0.5, so we don't get any false detection of pieces. And then on the left here, we have a picture of the warped board, and then you can see the car here, and then it says it's on top 28, the top right, which is based on kind of what player's piece it is, so we can tell that. And then using the centroid of that piece, we can compare it to where we want it to be, so we can find kind of tolerance, and then if any pieces get moved around, we can correct that easily. So for the user interface, we wanted to focus the design on more of how the player interacts with the system rather than kind of the layout that it has. So here we had 3 options that we were going for. First one, which was having one computer and the players would pass around with the mouse to play the game. And then the other 2 options were multiplayer options, one with WebSocket and then one with Python socket. WebSocket is just based on a browser, so you don't need anything installed. You just open a link and it takes you to the browser to play. And then Python socket is you need Python installed on every computer to be able to run that. And then with our decision matrix, we found out that WebSocket multiplayer was the best option to go with. So here's just kind of initial layout that I had just for the user interface. Board on the left side, and then on the right side, you can see alternatives. You have buttons where you can take your actions and then menu that. So here is the setup screen initially. So you can select the number of players, and then on the right, after you select the number of players, you can type in their names. You can select what tokens they are, and then you can also turn on and off some additional house rules like auctioning or free parking. And then here is the board after you start up. So here's just right after you start up the game, and then on the right there is a picture of the auction menu. So if you don't buy a property after your turn ends, it goes in an auction menu, which every player will bid a certain amount to be able to get that property. And then here's a couple of pictures of menus that can pop up if you click on the button. So you have the trade menu, you have the mortgage menu, and you have the unmortgaged menu there. And then here's just kind of a game state that we had. So you can see for Mediterranean Avenue, Baltic Avenue, they have houses and hotels on there. And then under each property displays the player's name that owns that property. So it's pretty clear. You can just look once and you can see who owns what. And then on the left side here, you can see that it says on Baltic Avenue. So it's just kind of more of a, you can be able to tell where you are at just right there. You don't have to kind of go look around for your piece that way. And then here's the proof of concept that we had for WebSocket multiplayer. So we kind of just made a simple square multiplayer game where all 4 of us were connected on different computers. And you just also just need the file with the HTML code, and you just click on that and it automatically connects you. One person does have to be running the server, and that's all they need.
Okay, so then just to start wrapping up here, here's our current bill of materials and budget. We were given $1,000 budget. We're currently at about $745. We got plenty of stuff to still buy, but we think we'll be sitting right with that $1,000 mark. Next steps, we want to be, we need to, for the mechanical system, we need to start working on an enclosure. So how we're going to connect all the different subsystems for each other. So Monopoly board, how that's going to sit, where the dice roller is going to go, and then how the force wire is going to fit underneath. Then we need to look at the belt connection system for the head. That's probably the next big step for the head. And then we really need to get going on the control system and cable routing. We felt it was really important to get a lot of the UI and the mechanical stuff done out of the way before we really dug into the control system, just because a lot of the decisions that were going to need to be made for the control system were reliant on what was going on with the user interface and the mechanical system. As far as the user interface goes, we need to start implementing the control code into game logic. The Python UI needs to be converted into HTML for WebSockets. So you saw that multiplayer demo there, but now we need to take all that Monopoly code and make it work with WebSocket. Other than that, just updating game logic, updating trading, and then any kind of bug fixes and testing. Thank you.
So, in this project, you're working with persons with disabilities. What was the biggest way you incorporated that aspect in the project, or was there something that you really thought about that would make this kind of stand out?
I think one thing that we were really worried about is we really wanted to preserve the game experience of Monopoly. So that's a big, if you look at our mechanical system, we really wanted it to feel like that they were actually playing Monopoly, not watching a robot play Monopoly. So being able to conceal the robot underneath, we thought was a really big plus for us. Along with that, we wanted to make the user interface really good and really integrated with the whole system, because if it's a pain in the butt to play, it's not even worth it.
How much do you think like each of these systems would cost? I know your budget is like $1,000 to, build one, I would think, but if you apply this to the market, how much do you think someone who would want this game, how much would they pay?
Yeah, well, so the biggest problem with our budget right now is all of these parts we're buying in very small quantity.
Mhm.
So, if we were gonna be mass producing this, you could probably cut the budget in about half off of just scale of market. But it wouldn't be cheap. And if you look at our background research, you'll see a lot of the stuff we did was a lot of hobbyist projects, because, things like this are expensive to build. But the general parts are cheap. There's just a lot of parts and a lot of things that need to go into it to make it work.
Yeah, that's what I was thinking. And so, sorry if I can continue.
Go ahead.
So if you have one setup, right? I guess if you have multiple players, would it be like each person had to have their own sort of board? Especially if they're like in different locations, or could you have you had that website where it was multiplayer and
Yeah. Well, I'll let Mason talk about this.
So with that, that's one of the reasons we kind of went away from the one computer, so that each player kind of had their own computer, and if they had some accessibility on the computer, maybe would use that. So just have the board around and you can kind of sit around with their own kind of laptops. So you don't have to necessarily look. So all the information is there for each player, and then you can look at individually they have their own properties and stuff that they can look at. And then you can see the board state.
Yeah, it's if you remember that being able to integrate eye tracking.
Yeah.
If somebody has an eye tracking system, this means that we don't have to actually code the eye tracking into our system, that they can use their specific system and still be able to play the game just by opening the HTML.
Thank you.
Yeah, I got a couple materials questions for you. You talk about, you mentioned PLA, right? And I thought we measured it in 3220 or 3210. But what was your design criteria for the part you're trying to make the PLA, and what's the driver for selecting PLA or some other polymer?
Pretty much we just selected PLA, or I kind of thought about that just as like 3D printing wise. Just because the component is so small, it's 2 inches by 1.5 inches. So it's a relatively small piece. So I'm like, well, it's probably going to be expensive if we're going to try to go to an outside source and really complex geometry, try to get something just so tiny. And I figured that just using kind of a PLA or 3D printing wise, especially because it's not going to be seen, and because it'll be in the house and in the Core XY underneath everything. So you're not really going to see it or interact with it. It'll just kind of be doing its magic, and you won't notice it at all. So yeah, it's just kind of just to simplify it, it probably wouldn't be as expensive.
Okay.
It's also incredibly light and very rigid. So for a system like this where we're moving mass around, being able to move such a light mass is a big plus for us.
Do you have like a design criteria for in terms of, you mentioned that being really rigid?
Yeah.
Do you have a specific value that you had?
Not yet, no.
Okay.
That's probably something that we'll dig into as we start to actually build the system. We want to get it mechanically sound before we start worrying about all that extra stuff.
My second question is the magnets that you're using. It's designed to be able to hold certain pieces, but.
Yeah, so I did, keep going.
Yeah, how about releasing that actual part?
So I did some initial testing, like we have our Monopoly board, I just bought some general magnets and then worked on trying to just line up a piece. I kind of took some like bottom pins or something and kind of stuck a magnet to the piece and then tried to see how it would connect underneath the board. And it worked relatively good, where I could move the piece kind of along a specified path that I wanted to move. But detaching from it was a little difficult. So we have an idea of to implement something of just another layer underneath the Monopoly board. That the one guy's video, he had, I think like a mag or a glass kind of surface over it, just to give it a little more rigidity, so that when it pulls down, it doesn't like yank the Monopoly board down and kind of make everything about it well.
Okay. And I think you can actually get magnets of different permeability, which could help. You know, you have to make a selection in terms of kind of what you just said, that test that you just called that sort of qualitative test.
Yeah.
But you can actually buy magnets with a very specific permeability, so it doesn't have that strong of a.
Yeah. Hey, I know we just kind of generally looked into it just to be able to make sure that magnets would be able to move it.
Yeah.
But I know we have future plans of looking into like specifically what magnets we want to use and stuff.
What were you into?
I know we had talked about, making custom pieces that were a little bit smaller scale, so we could kind of add like a little housing spot for the magnets. But right now, we don't have too much into that as well. We just kind of wanted to start to get the actual mechanical system working before we like, actually physically get that.
Okay, we'll stop there. Thank you so much.
So we are the second. My name is Jocelyn Cotty. I'm the technical.
My name is Eric Wertz.
So we did our introduction.
The problem statement for this is that we needed to create a functional Monopoly board game that utilizes eye tracking to enable fully accessible gameplay without removing the physical board game experience. Now, some of the background for this is that traditional Monopoly requires rolling dice, token manipulation, money handling, dealing with all these small moving parts. This can become an issue for people who have issues like their fine motor skills, or they just don't have like good hand-eye coordination or other disability issues. There's a couple of existing solutions for this. Mainly fully digital game, but this removes the human element of the game. You might as well just be playing a video game online, or you have the modified physical games where you're playing with oversized pieces or relying on the help of other people to be able to do some of the more fine motor skill movements.
So at risk of sounding like a broken record, we're gonna go over the requirements and constraints of this project again. So accessibility wise, this project needs to be completely click-based inputs for the graphical user interface. It also has to be compatible with eye tracking software. So no fine motor skills are required despite having to actually set up the board and place the pieces. We also want to preserve the actual gameplay component of this project. We want to use the real board as well as the real tokens that come along with the board. And we also want to make sure that the token movement and the dice rolling are totally visible. We don't want you to have to stand on a stool to be able to actually see something working. We want it to be on a tabletop, completely within the line of sight. We also want to have a multi-user interaction with it. Each player gets their own device, so we don't have to worry about other people fighting over one eye tracking software. Everyone can have their own device. And we also want to implement simultaneous inputs. So if a piece is moving or if someone else is rolling, other people can worry about auctioning off a location or just something else that doesn't have to deal with the person that's actually having the turn. And then for the automated gameplay options, we are fully automating the token movement as well as the dice rolling and reading. Because those are basically the two main components that are moving. And we also want to completely track the position of the pieces throughout the entire play of the game. Some more constraints, on the more mechanical side, the mechanism must fit within the footprint of a basic Monopoly board. Given some wiggle room, I suppose, for electronical components being able to fit in there. We want to also limit the vertical height. Again, like I said, you don't want to stand on a stool to be able to see the top of the board. You want to be able to see it just on a basic tabletop. And we want to enclose the moving parts. Apart from it being aesthetically pleasing, enclosed moving parts means more safety when the parts are actually moving. Reliability and durability, it must be reliable over an hour-long gameplay at minimum. And we want to reduce the wear and recalibration when we're actually working. And for the user experience, we want to maintain a social physical gaming experience. We want to be able to interact with it just as well. And then we want to also have a simple interaction with the click-based user interface.
On the electrical side of the game, everybody needs to have their own display so that they can all do their things at the same time. So you don't have to wait for your turn with the screen to go do something. So Monopoly has a lot of actually think outside your turn, such as offer to buy or sell properties to other players. So they all need to be able to do that in sync or like at the same time without having to wait for other people to go through. And we also need to make sure that we don't lose information that you are say bidding in an auction and doesn't just not go through, because that sucks. The players just not have your actual fees what it's wanting to do. And you have to do all this under the senior design budget, which is $1,000. We want to maximize the amount of off-the-shelf components, just that there's number one less stuff that we have to design, test, and build ourselves and just get off the shelf. And we need the whole thing to be serviceable and maintainable. So we want You open up the board, go in and fix things if they go wrong, rather than trying to completely throw it out and get new out the board. So for background research, one of the things we were looking into was the dice roll. And when you think about dice, there's two times you're gonna use dice, whether you're playing board game or gambling. Gambling, they got that figured out. So we found a patent for a dice rolling machine for a craps game, where it automatically rolls it using actuator, and it then uses a camera system to be able to read the dice and be able to accurately put what the roll was. And also with it being designed for gambling, we know that it is a proven randomized system. And then the other research that we did was
Did some token research, for patents going into that, we were looking at kind of two components. We want to magnetically actuate the game, and we also want to figure out a way that we can use a belt-driven or a chain-driven movement. So these two components, as you can see, figure one is the magnetically actuated game. That's kind of a proof of concept that we can actually use magnets underneath the board to move pieces. And for the figure two, as you can see on the bottom right, that is proof of concept that we can actually get a belt or chain to drive around a specific closed path. And more background research we did, we dived into some articles about the belt and chain drives as well as the eye tracking software. As far as the belt and chain drives go, the article kind of dove deeper into what you would use each for basically. And due to the lower levels of noise, friction, and maintenance, I feel like for our project, a belt-driven mechanism would be best. And as far as the eye tracking goes, that was deeper diving into what makes eye tracking special and what you need to have in order to make a good eye tracking software. Large uncluttered interfaces are obviously the best, because when you're looking at something, you don't want to look in something really small and get lost in translation. Yeah.
So we started with some initial designs. We have a couple of designs to start off for our token movement. We first thought of a general like XY axis scaling system. This is a pretty simple rising forward movement. You know, the pieces will be coupled with a magnet underneath the board and then generating XY entry system. We had some pros. It's scalable for a lot of players, fewer failure points, less materials and electric components, just two motors to drive each axis. The cons that we thought of is collisions and the inconsistency of the pick and place. A little bit more difficult to code because you have to monitor the exact position of every piece. So that's ultimately why we decided against this design, is because of that inconsistency of the pick and place and the difficult coding process. Another option I'm thought of is a center driver arm. This one is also pretty similar in why we decided not to go with it due to its difficult coding and manufacturing process. The one big pro of this design though was that it can do cross-board movement versus going along a path or anything. It can pick it up and move it all the way across the board by going parallel, diagonal. How many directions? Across the board. But ultimately, we decided to go on with our next design, which is what we ended up going with, which is our 4-track magnetic belt-driven system, where every single piece is going to be driven by its own independent belt loop underneath the board and then connected with a magnet underneath. It will never decouple from its magnet, and so that aids with the consistency of not having any sort of pick and place movement. So it just sticks with it, and then every motor will drive its own. So yeah.
So for our initial dice randomizer designs, the first option that we had was the dice tower. The dice are going to be raised on a raising platform. It hits the edge of the tower and it tumbles down the tower to the platform below. And that is where the camera would be able to read the value that the dice actually has. So pros of this option are it's mechanically simple. It's been proven before. Dice towers are used in a lot of different board games. It's easy to service and can be designed with a certain visual appeal to make it as interesting or as uninteresting as you want. And it also allows control of where the dice land, which maximizes your chance of actually reading the dice correctly. Some cons are the dice could possibly get stuck on this tower. It's bigger and therefore it kind of goes against what we wanted with a smaller vertical height. And it also slows the gameplay by having to actually reset the dice. So this idea was rejected due to the time it takes for actually lifting and lowering and resetting the dice.
And then the second option for dice roller was using a dice popper design. We're using a force to move the dice from below, having a rotating motor that moves the platform up and down, that allows the dice to be thrown around the inside of the dome. And with it being a transparent dome, you're able to see the dice clearly and be able to know that what the game is showing is what was actually rolled. And the pros of it are that it's compact, it has a fun visual feel, seeing the dice popping around, and that it is really quick to do multiple succession of rolls if you roll doubles. Some of the risks are if the dice could potentially land on top of one another, the vibration of the moving platform up and down could present some issues. And it could also require some more precise mechanical refinement to be able to get consistent rolls. So as connecting them together, because each device has to connect to all other devices so they all know what they're doing. Our first thought was just to plug them into one another. This would work. It's pretty simple, but there's a couple of problems. Number one, you have to have these cables going from device to device to device to device, and that's number one, extra hardware. And number two, that looks ugly, and it's a lot more elegant to just have them connect each other digitally. The other thing is if we don't have the same type of ports on their devices, because we're designed this to be compatible with pretty much any device that has eye tracking capabilities. So as long as if their devices don't have the same ports, we don't want to have to go to the code and have to figure out, okay, which port are we using, how do we connect between these, and just that goes to that's very suicide times. Our second option was TCP clients, which number one pro for it is that MATLAB has inbuilt TCP capabilities, which we're planning to use MATLAB just because that's what we all know. You don't want to learn about the programming language on top of the rest of the project. But on the other hand, every user then has to install the MATLAB compiler, which although it is free, that is an extra install step, which makes more work to do. And also, since TCP is just client to server, we're running each where we have to loop through each person want to send something to everybody. So if we want to like share the entire game stage rather than just talk to one, we have to do each of those back to back, which slowed it down. So what we went with at the end went for WebSockets, which used a basic Python server to just connect from MATLAB backend to an HTML front end. This allowed everybody to just open it up in their browser of choice. They don't have to install anything except the person running the program. And it's more work to set up, but it gives a cleaner result. And so the way that we came to all those different conclusions was by doing a decision maker. And we started out doing a top level where we were looking at dumping mover, our 3 different options, and dice roller with our 2 different options. We came based off these criteria, we came to the 4-track magnetic and the dice popper. And then from there, we broke those down into smaller, more targeted decision matrices of going, should we use chain or should we use belt? And then the different ways that the actual popper would be activated. And then these are the different options that we came to for that. So currently with the dice popper, which we have right up there in the front, here's a little bit. So we have manual control of a roll where you're able to just press button and the whole thing will pop up and down as you go it. And doable. There's a wide angle camera above it that will be able to look at the dikes. And with the clear enclosure, you can see it easily. And the actual platform itself has sloped sides so that the dikes are able to come back down the side of it.
So token sleds, the pieces for the Monopoly board are not inherently magnetic, so we had to come up with an idea to actually make them magnetic. I'll pass this around. These are the sleds that are going to be used. As you can kind of see that there is a mounted magnet to the bottom of the sled. And it's customized per piece, so it's not just one universal piece sled. You can just kind of mix and match with whatever, well, I would say mix and match. You can use it with whatever piece that you're using. And then as you can also see, as you look at it, there is a lip to prevent the movement of the piece. And looking forward, we want to integrate something to the bottom of the actual sled to minimize friction. So we're thinking about adding felt to it just to make it smoother around the board. Then we had a few prototypes that we wanted for proof of concept. The first one was a pulley layout prototype. It determines the pulley layout with the path constraints. So it's dimensioned to a corner of a Monopoly board. We want to make sure that the pieces stay within the board, but we also want to make sure that the pulleys are positioned nicely so that everything fits. So the concept that was proven, the 4 pulleys can fit into one corner, and we figured out the dimensions to make that happen. And we incorporated those into our SolidWorks design. And this was used for the final design and dimensioning. Our next prototype that we used was a stepper motor driven belt around a track, as you can kind of see up there. We also added the standoffs that we'll be talking about a little bit later to it quite recently. But the concept that was proven is we can get the belt to move around a closed track with a motor driver, pulleys, and just the belt loop. Some improvements that we need to make to this design is to determine the belt tension over a long distance. So we need to make a prototype that actually spans over a long distance so the belt actually works. So this is a video of it working. As you can kind of see, the belt is moving relatively fast. It's kind of variable speed. You can make it go as fast or as slow as you want.
So onto what we're actually using as a configuration for the belt movement itself. We'll be using 4 DT2 6mm timing belt loops, which will be spliced together by hand. We'll be using 4 11 separate motors to drive every loop. We did a dynamic analysis of the belt system and to determine the necessary torque from the motors. So that's why we decided to go with the NEMA, because it was capable of the torque that we determined that we needed. We went through a bit of the actual analysis in the appendix of this presentation. Every pulley, all the drive pulleys will be 24 teeth. This will give us 16 mesh, which is standards between 7 and 9. And then we'll have 3 22 either pulleys in the other 3 corners to complete the loop. And then we'll be adding limits, which is along the length of each belt loop to correct the positioning during the gameplay. Then the next things that come up are how the pulleys are mounted to the system. The pulleys are going to be set screw fixed to 5mm rods. And then those are going to be sandwiched between 2 brass bushings between the 2 plates. Brass and steel have a pretty low coefficient of friction, so they'll be able to function basically as bearings, but in a more custom state. And then during our actual assembly process, we'll be finishing the remaining surface between the steel and the brass to make it as low as possible for that friction. And then we'll be using powdered graphite to lubricate the other moving twisting components. The actual magnet standoff that we'll be using a 2mm rod would be fixed to a flexible 3D printed resin standoff. The standoff is going to provide some clearance around the lips of the pulleys and centering around our guide tracks here that are going to be CNC'd into the bottom of our lid. That's going to be holding everything together, and then the magnet will then ultimately connect through the board onto the sled. Up here is what the standoff current design is really looking like. And then we'll be using like E6000 adhesive to put everything together because of its flexibility during its completed curing process. And then our mounting housing that will basically look like this. It's about 4 inches tall. The housing will be 3 flat sheets of plastic with 4 side panels to hold everything together. The lid will hold the board itself and then have the guide tracks underneath, and then we'll also hold the top brass bushings for the pulleys. And then the middle board here will be basically where everything is mounted to have the stepper motors hanging from the bottom of it, fixing the bottom of the pulley rods, and then it will also be pulling the lid switches. And then we'll have a false bottom there to hold everything else in place and conceal all of the wiring and keep all of the movements. And then here's kind of just an exploded view of how it's going to look without the lid obscuring the top view and then those 2 side windows.
So this is our current state for the code. Is each user gets their own HTML file, which talks directly to the Python. Python basically takes whatever the user does on their HTML and sends that to MATLAB, which MATLAB will then process it and send it back. One person has the, whoever's playing the banker or the host will have the server that they're running on their computer. Next slide. The entire game state is held in a structure, which includes all of the, so basically a big list of variables that contains all the information about the game. Every time someone does something in their HTML, that'll be sent from their HTML through WebSocket to Python. Python puts together a list of things that have been done, sent it to MATLAB. MATLAB calls functions, which there's just a large list of for each thing that can be done, which takes game state and it outputs the new game state for whatever actions they're taking. This is a lot better than our previous version, which had loops, because if someone does something like initiating a trade, then other functions can run in between those before the other person has to reply to it. But before, if someone initiates a trade, then has to ask the other person, are you going to accept or reject the trade? And everything's going to halt while you're waiting for that. So breaking down the functions lets every other function can run until that response function comes up in the listing. Should make the whole thing flow a lot smoother. But this is our concept for the GUI. So it's just going to be a list of all of the stuff at the top, where everybody's position is, how much money they have, and a bunch of cards at the bottom. Those cards are going to be based on the title deeds from traditional Monopoly. And this bigger version of the here has, the name of the property, what the current rent is. Each card will have on that buttons to be able to do actions with the card. So rather than have to open a separate menu to offer to sell property or offer it off, you just click on it on the card itself, which just kind of smooths over that aspect of it as well. And
Right, and then for taking that as a proof of concept and moving it into the HTML web base, we created this mock-up of a prototype that is actually fully working, where you can hit roll dice, it rolls them digitally at this point, and you can purchase properties, you can see the other players, buy, sell, and do all of the things that you need to. And then for the code part of the dice roller, we are using an ESP32S3 camera to capture the image with a wide angle lens so that we can see the whole thing while still being up close. We're using outer edge block detection algorithms to be able to pick out the individual pips on the dice and then cluster them together to get the rolled value. And then it rejects oblong circles on the sides so that we don't get weird rolls of it thinking that dice just rolled like a 9 or something by being able to read some of the ones on the side. So then for next semester, our main goal going into it is right now we have our individualized subsystems, and integration of those is going to be key. So being able to get all of our different parts to work together and talk together is going to be our first step going into it. And there'll be when we're going through finalizing the design and, then also ordering materials too. And you see we have everything laid out so that we leave ourselves plenty of time at the end to be able to prepare our presentation, get final results, do all of our final testing, and not run into a crunch at the end.
So this is our current bill of material organized by subsystem essentially. As of right now, this is how everything is totaled out in quantities and in general amounts from what we've been able to find online. Our subtotal was $666, and then we added some calculations for tax and shipping. We are now at $970, which is going to be below the $1,000 limit that we were allotted. The appendix, which is just general in-depth market information, if you guys want to look at it later. Nomenclature about some of the stuff that we're going to be talking about later in it. The maximum acceleration that the belt and magnet can then hold. These are the belt dynamics that I was talking about earlier, with us choosing which type of motor that we were looking at. And then we had a spacing analysis on how to track where the pieces are. And then we did a belt adhesion test to test how much overlapping space we need in adhesion to keep the belts together.
You got time for a couple questions.
I'll go. So I'm imagining, based off of your description, is that the belts, the four belts are just gonna drag the pieces along the board. Do you think, I guess my first question kind of based off that, do you think like over time that will kind of wear away like the top of the board? Like, the different descriptions and stuff? Because it will like rub off.
On the top of the board?
Yeah, as the pieces.
The belt slip that we're gonna be
Okay.
trying to put on the indicate that.
Okay.
I imagine the surface of the board will be sound enough to be able to play in the first place, that it should be able to. Nothing friction.
If there is some rubbing though, do you think like it's easy to take apart the board and just kind of put that, like replace the top?
Yeah, the
Okay.
board is not gonna be connected to the lid in any way, you can just pull the board off. So as a disassembled system, you can put the Monopoly game away completely in its given box and then have that actual system self-separate.
Thank you.
I got kind of like a tag along question with regards to the belt. Do you know what type of tension you're gonna need on those belts?
Yeah, that went into the belt dynamics. We found that we needed like preload of about 1.7 pounds force, which is what we found based off of some documentation of the belt that we bought, going with a 30% of the working tension, the rated working tension we chose for our preload. Just how we came up with that.
And then to tie that into like, you mentioned light. So like, did you consider like the stress relaxation of the belt? You mentioned it for like the actual game play, but how about over like years? How long do you expect those things to like last?
Initially, we're going to be using smooth idlers, with teeth against the smooth idlers, which is not very good for the belt life. So we did switch to the teeth idlers to increase the belt life. Belt life calculations are not very easy to do, but doing like a comparison, you're able to say that it has improved by like this much, but not an actual like measurement. But just of how much we increased it by.
So because rather slice the belts ourselves, we don't come in, every possible length. So if we get the right size, we have to do that ourselves. We don't have years actually test.
Any last questions? All right, thank you so much. Yeah, turn this on.
Are you gonna come to the thing tonight?
I'm not gonna be able to make it.
Oh, okay. Okay, well, I hope you have a good break.
Yeah, you too.
Really?
Reflexive.